Today we will be completing lesson 5.4. In the previous lesson, we determined how to have expression in log form, and also to evaluate logarithms. We also learned that logarithm is used to describe the inverse of a power. For example, inverse of 10 to the power of x is a log to the base 10 of x. For example, what we did learn is that from here, that the inverse of 10 to the power of x is equal to log 10x. We also learn how to convert exponential to log, or writing different expressions. And we learned that by y, here, y is equal to log 5 to the x. It's equivalent to exponential y, 5 to the y equals x. Another way of writing that is to look at if we have a. So essentially, if you're looking at the bases are the same for the log and the exponential. This would be your exponential. This is your log. So the bases are the same, but the exponent here, the exponent is would be equal to the log. So base is the same, the exponents are equal. And let's look at the actual example. We have log 10 to the 100 is equal to 2. In other words, we're saying log of base 10 to the 100 is equal to 2. Because if you write this exponent now, it will be 10. This is your exponent. This is your log here. This is also the exponent here. It's asking how many times do you have to multiply 10 by itself to give you 100? The answer is 2. So this is exponent here. So that's what we did on the previous lesson. We looked at writing expression in log form and evaluating logs. We learned that if you have log e to the bn is equal to n. So we use this principle a lot. For example, if we have log 3 to the 3 to the power of 6, it's 6. So we'll be using this frequently and to evaluate log other than base 10. So remember, we're using this a lot. We're also using b to the a is equal to c because log b to the c is equal to a, so the exponent. So for today's lesson now, we'll extend that, and we're going to use the benchmark to estimate the value of a log. And then we will look at the characteristics of the graph of a log function. Now, let's look at the first example. To the nearest tenth, estimate the value of log 2 to the 10th. Now, if you look at this log, 10 cannot be written as a power of base 2. what I meant by that. Let's say we have log 3 to the 81. Now 81 could be written as a power of 3. So we can say 81, say here, 81 could be equal to 3 to the power of 4. So answer will be 4. In other words, we could have written this. Oh, so it's be 4. But we cannot write 10 as a power of 2. We cannot write 10 power. Same as how we could write 81 as a power of 3. We cannot write 10 as a power of 2. Because it will be an irrational number. So we can see here 10 cannot be written as a power of 2. What you'll have to do is to develop an estimate, or what we call benchmarks. We cannot have a precise number, so we can have benchmark. So we use benchmark to estimate the value of the log. We'll have to use an estimate now. Now, if we look at log 2 to 10 here, it has base 2. See here, 2 to the 10. The base is 2. So what we want to do is to find the power of 2 that's closest to 10th as our benchmark. So we use the power of 2 that is the closest to 10 as a benchmark. So what we'll know that 2 to the power 3 is 8, and 2 to the power 4, 16. So we can conclude that log 2 to 10 is between log 3 and log 4. So we can say log 2 to 10 is between log 4 and log 3. So those are our benchmarks. So now we are going to say now look, 2 to the power 3 is 8. Now 8 is closer to 10 than 16. So 16 is much farther away from 10. So 8 is closer. So now we will use log 3 now. Now, if you look at 3, 2 to the power 3 is 8. So it's not close enough. So we try to take it to a decimal. So we do an estimate. We said, okay, let's try 3 to the power so 2 to the power. So we know 2 to the power of 3 is 8, so we type 3.3. So I'll go to my calculator here, see how close, how close it is. Let's see. Use my exponent of 2 to the power 3.3, give me 9.8. Now, if I try 3.4, let's see what happens here. So we got 2, 3.4. So it's over. So 2 to 3.3 is closer to 10 than 2 to 3.4. So we can conclude. So we said log. So we do make an estimate. So this is an estimate. We can conclude now. Log log 2 to the 10 is equal to 3.3. So I'm using my exponent here, 3.3, approximately. Oh, it should be an approximately here. We'll put a dot there. Symbol mean approximation. So approximately. So the process is, number one, we find out first if we can write 2 to the 10, in this case 10 is a power of 2. Since we cannot use a benchmark, and so we use the power of 2 that is closest to 10, closest possible. Then we know that log 2 to the 10 is between 4 and 3. From here, we said that 8 is closer to 10 compared to 16, which is much farther away from 10. So we'll use 3 as our log. But log 2 to the 3 is equal to 8. So it's a little bit farther away from 10. So we try to get as close as possible to 10. So we do an estimate. You can try 3.1, 3.2, 3.3, 3.4. And then you'll know which one is closest. The one is closest will be your log. So we put an approximation here. So we can conclude that log 2 to the 10 is approximately 3.3. Let's try another couple more. Okay. Group a couple more examples here. Okay, get my okay. Let's look at the first one here. Look at 2, log 3 to 12. Now, 3 cannot be written, sorry, 12 cannot be written as the power of 3. So we cannot write, so we can do it here. 12 cannot be written as a power of 3. So we need to use benchmarks. Use benchmarks. To estimate. estimate the value of log 3 to the 12. So find powers of 3 that are closest to 12. So we know 3 to the power of 2 is equal to 9. And 3.3 is equal to 27. Right away, we can see 3 to the power 2, or log 2, is closer to 12 than log 3, which is 27. So 9 is closer to 12, and 27 is closer than 27. Now, so we can see here log 3 to the 12 is between log 3 and log 2. So remember using the exponent is the log. So we'll use 2. So 3 to the power of 2. Now we can try 2.1. See what that gives us. 3.1. So 3 to the power of 3.1 give us, oops, it's 2.1. 3 to the power of 2.1. Give me 10.05. It's pretty close. But let's go one step further and try 2.2. Pretty much for. So 3 to 2.2. Now let's try the next one. 3 to the power of 3.3. Oops, nope. 2 to the power of 2.2. Let's replace that. 2.2, and then we have 3 to the power 2.3. Now notice 2.3 is 12.51, 11.21. No, 11.21 is much farther away to 12 than 12.51. 12.51 is only 0.5 away, 0.51, while this is roughly what, 0.79 away. So we'll use 3 to the power 2.3. It is closer to 12. So we'll put here closer to 12, and then 2 to the 2.2. So we can conclude that log 3 to the 12 is approximately 2.3. So step 1, find if this 12 could be written as a power of 3, and the answer is no. Therefore, we use benchmark to estimate the value of log 3 to the 12. Then we find powers of 3 that are the closest to 12. So we have 3 to the power 2 is 9, and 3 to the power 3, 27. We know 27 is much farther away from 12 than 9 is. So we can conclude that log 3 to the 12 is between 3 and 2. Since 3 to the power 2 is closest to 12, we use 3 to the power 2. Then we do a series of calculations to find if it's 2.1, 2.2, 2.3, and we discover this 2.3 is closer to 12 than any other one decimal place. We leave it at 1 decimal place for now. Let's look at one more example. In here, we cannot write 100 is a power of 2. So we can say that right away. We can say 100 cannot be written as a power 2. So we'll use benchmarks to estimate. First of all, we try 2 to the power 6, which gives us 64. Then we have 2 to the power 7, that gives us, what, 128? So we can conclude the log to 100 is between 7 and 6. Then we go ahead and what we find that we can get closer, 64, 2 to the power 6. Now, 2 to the power 7 is already above 100. It's way far. So we cannot, if you go 7.1, 7.2, it will still go higher and higher. So we'll have to use 2 to the power 6, or log 6 in this case. So we have 2 to the power 6, and we try different ones. We tried, I'll make an estimate here, maybe 6.5. And see what would that become? 2. So we have 2 to the power 6.5 gives me 90. Let's go to the next one. 2 to the power 6.6, 97. Okay, much closer. So we can eliminate 6.5 because it's much farther away. Then try 2 to the 6.7. Now that's much further away from 100 than 97 is. So we'll use 2 to the power 6.6. So we'll use that 6.6 is equal to 97.00358. It goes on. And we have, if you were to compare it, 2 to the power 6.7 is equal to 103.96, which is much further. So we can conclude that log 2 to the 100 is approximately 6.6. A couple of other examples I would like you to try, and then you'll try that in your book. It's question 15. So we'll apply the same process. We cannot find, we cannot write 6.5 as the power of 2. So therefore, we look for the power of 2 that's closest to 6.5. So we know 2 to the power 2 is equal to 4, and 2 to the power 3 is equal to 8. So we can tell right away that log 2 6.5 is between log 3 and log 2. Two to the power 4, now they're almost identical way, but notice 2.3, 2 to the power 3, this is much greater. So we will not consider that because it's greater than 6. This we can increase as close as possible to 6.5. So we'll try 2 to the power 2. I'm just doing a guess here, 6. Let's see what it is. I'll just notice I'm just doing an estimate. 2 to the power 2.6, 6.06, then try 2.67. So 2 to the 2.7, 6.49. That's much closer. It's not above it. It's much closer than 2.6. So we can compare them. You can write it down here. 6.06 and 2 to the power 2.7 is 6.49. Goes on. So this is much closer. So log to 6.5 is approximately 2.7. So follow this process when you ask to find benchmarks. The other example, I'll let you try that one in your textbook. The next set of questions we're looking at, now we are going to go into graphing. Identify the characteristics of the graphs of a log function. Here you're asked to graph y is equal to log 3 to the x and identify the intercepts, the equation in the asymptotes, and the domain and range of the function. Now, recall when we looked at comparing exponential and log function, we said that log is the inverse of exponential. So we'll demonstrate that in this lesson with this question here. Now I went ahead and create a chart. Whenever you create a table of values. Now here we have y to log 3 to the x. I just select a few coordinate values for x, and then I'll solve for y. So this will give me my y value. And I'll plot my graph, and I'll do the same thing here for the inverse. So the inverse of log 3 to the x is y is equal to 3 to the power x. Remember, we're using our fact, which is y is equal to 3 to the power x is equal to log, this is your base here, log 3 to the x here. Okay, in this case would be y is equal to x, using that principle here. So the inverse. Now, they are equal, but I'm going to use the inverse now. Y is equal to 3 to the x. Okay, let's graph y equal 3 to the power x. This will give me 3 to the negative 2, which is 1/9. So this is my exponential function. This is my log function. And 3 to the negative 1 going to give me 1/3. That was 0 is 1. The 1 is 1. And 3 to the power 2. Oh, this would be 3 here. This would be 9. If I were to plug those points here, negative 2 should be about here, is 1/9. Very tiny. Negative 1 would be 1/3. 0 would be 1. 1 is equal to 3. So this graph is going up. Y is equal to 3 power x, which is exponential. Now, find log 3 to the x. Now my value, okay. So if you look at, so we have log 3 3 to the 3, here, which is power 1 is equal to 1. Now this will not work. So 2 will not work. So we have to, because we have to do an approximation there. But log 3230 is equal to 0. X equal to 0, that will not work. So we go to, now none of these will work. Log 3 to the x will not work. So what we'll have to do is to take the inverse of these as our x values. So if I try to use this way, you could have done it this way, but the values for your x, because we know our log function, unless it's a transform, will not shift to the left. So this table here is much difficult to do. It can be done, but you'll get a lot of approximation. And this is, you'll find, is undefined. Doesn't exist. So what you'll do, since we know it's the inverse of the exponential, we can use the x values, sorry, the y values for here into our x. So we'll replace all of these now. You see, I can show you if you try this, it will work, but remember these are all undefined. For example, we have 3 here will give us 1. So we can see our graph here, but we'll create another table of values using this now as our x values. So let's try. So replace this now. So y log 3 to the x. So I'll interchange the coordinates. So I'll switch these around. Basically, you're switching them around because it's the inverse. So I'll show you it will get easily calculated. So we have our x, and we have log 3 to the x here. So my x here is 1/9. X is 1/3. X is 1. X is 3. X is 9. So log, and in this case, you'll be using this principle where you have log b to the bn is equal to n. So log 3, now this 3 becomes 3 to the -2. So the answer is -2. So my y value now, or to draw a line in here, oops, my y value y value. Now go ahead here and log 3 to 3 -1. This is my x. And this will give me -1. And log 3. Now we can put here 3 to the power 0 is equal to 0. And log 3 to 3 to the power 1 equal to 1. Because I'm making this a power of itself. I can write this as a base 3 here. and log 3. Now 9 could be written as a power of base 3 to the power 2. Now I have my x and y coordinates. It's much easier to find the exponential and then switch or interchange. This becomes the x for the log. These are all the x's and these become the y. Now I'll plot these points. 2, so I have okay. So these are my coordinates. 1/9 is -2, so 1/9 x is 1/9, -2 is down here. 1/3 is -1. X is 1, y is 0. X is 3, y is 1. X is 9, y is 2. So this is my graph. Now that becomes your log 3 to the x. For the log function, notice there's no y-intercept. If you look at our graph right now, there's no y-intercept for a log. So we can conclude no y-intercept. Let's compare to the exponential. There is an x-intercept at 0, 1. Sorry, a y-intercept at 0, 1. So for exponential, there's a y-intercept at 0, 1. There is an x-intercept at 1, 0. There's a vertical asymptote. The graph doesn't touch the y-axis. So vertical asymptote at x equals 0. Doesn't touch. Okay. The domain, now graph goes from 0, never touch it, is greater than 0 to infinity. So x is greater than 0. And finally, our range, there's no limit from -infinity to infinity. We say y set of real numbers. So the characteristics of a log function is no y-intercept. There is an x-intercept at 1, 0. A vertical asymptote, x equals 0. The domain, x is greater than 0. And the range, where y is a set of all real numbers. Look at one other example. Use a table of values to graph y equal log 5 to the x. Now, here we're going to apply one of the rules for log other than base 10, which is log b to the n is equal to n. So we have a common base, and the exponential will give us our log. So we'd apply this in this case. Here, I've selected these x values because they worked out nicely. And one of the things you could do to make it easier for you to work is to look at your base here and then find multiples of that base. And start from 5 to the negative, in this case, 5 to the negative 1. We have 1, and 5, oops, and 5 to the power 1, 5 to the power 2, 5 to the power 3. Because this becomes, satisfy this form, where your exponent now becomes your log. So let's look at 1/5 now. We have a log. Now 1/5 is 5 to the negative 1, but it gives me negative 1. So that's my y value. Then I look at log 5. Now 5 to the 0 is equal to 1. So I have 5. I should put that here. 5 to the 0 is equal to 1. Then we have log 5 to the 5 to the power 1. Oh, this should be 0 here. 5 to the 0 is 1. Is 0. Should be 1 to the 0. Missing here. Okay. Okay. 5 to the power 0 here. It'll give us 1. And 5 to the 1 will give us 5 here. That should be 0. Okay, it should be correct. 5 to the 1 here will be 0. Now this would be 1. It's 5 to the power 1. Then log 5 to the 5 2 is 2. Log 5 to 3 is 3. Okay, now we plot those values. 1/5 is negative 1 here. 1 is 0. Should be closer. Okay, this is 2 here. This is 1, 0 here. Then you have 5, 1, which is there. Which is, we have 25 is 2, which is, this is my graph. So log 5 to the x equals y. So the question now, identify the intercepts, the equation asymptote, the domain. The intercept here is 1, 0. X-intercept at 1 or 1, 0. Asymptote x equals 0. Doesn't cross the x-axis. Sorry, the y-axis. Doesn't cross the y-axis. 3. We have the domain. Domain is from 0 to infinity. X is greater than 0, and the range y is a set of real numbers. So from negative infinity to goes up to infinity. Okay. So your task is to complete the assignments in your example booklet. Just a reminder, that's your example booklet. And you are to complete, lesson 4. So for practice, try question 3 and 4 on page 379, and lesson 4 in your booklet. And you want to complete lesson 4. Now there are 2 pages, pages 15, 16, and a few examples you can work through, and the next page.